Good afternoon, everyone. So today I will talk about accretion and ejection around black holes, mainly low mass and supermassive black holes. I will talk about, and then I will talk about my current and ongoing works. So, as you can see from this figure, matter falling onto a black hole forms a disc-like structure, and it can also produce jets. So, along with black hole, companion is also very important because without this disk we cannot see black hole. It is completely black. So, both are important. However, in this talk, I will mainly talk about this isolated black hole where disk has already formed, and jet is also there in some cases, or maybe not appeared in some other cases. So here is the motivation of the talk. So matter falling onto a star was studied long ago by Bondi in 1952, but Bondi's solution was only for spherical accretion, where matter is radially falling onto a star, and the radiation efficiency was quite low, so it cannot explain this quasar luminosity or the radiation which is coming from the black holes. Therefore we need something else. In 1969, Lyndon Bell and his collaborators, they showed that accreting matter forms a disc-like structure, and later in 1972, Bardeen studied a particle orbit around a rotating black hole, and Wilson at the same time did hydrodynamic simulations in Kerr geometry. But as we saw from Bondi's solution, we need something else. So what is that? In 1973, Shankar Sunaev and Novikov Thorne, they proposed that classic model that matter should transport angular momentum to feed a black hole, and this mechanism can produce powerful emissions. So this matter falling onto a black hole forms a Keplerian disk, but that Keplerian disk which produces multicolor blackbody spectrum. Later, Sunaev and Trumper and other observers realized that one component, that is the standard Keplerian component, is not enough. So to interpret observation, they need something else, some more component. So in 1977, Vishnupati Kogan and his collaborators, they found that viscosity can change during the outburst phase of the black holes, and they can trigger this powerful emissions. So as the Keplerian disk cannot explain the observed data fully, Sunaev and Titarchuk, from their solution, they found that hard X-rays are needed to explain the observation. So along with soft X-rays, which are coming from the Keplerian disk, hard X-rays are also needed, which are mainly coming from the inner region of the disk, which is very hot. Later in 1995, 1994, Chakraborty and Titarchuk and Narayan, they proposed advective flow models, and it can explain the observed feature both from hydrodynamic and radiative transfer solutions. In 1996, Molteni proposed that the observed periodicity in the light curve can be originated from the oscillation of the Compton cloud, or it can be from the oscillation of the shock. So what we see, so as I said that today I will talk about this isolated black hole only. So this black hole, as you can see, has mainly when it is cold, that is in quiescent state, it can the spectrum is mainly dominated by the disk blackbody component. However, as the matter starts accreting and black hole activity starts, this become hot, and this inner region of the disk produces power law spectrum. However, there is also another component which is basically jet component. So jet can also behave as a hot Compton cloud, and it can upscatter the photons coming from the Keplerian disk, which are soft. So these are the components generally observed in black holes outburst time. However, along with this black body, power law and jet components, there are other spectral components which are non-thermal emission. It can be due to synchrotron, or because of this presence of magnetic field in the jet. So this non-thermal emission I am not going to consider in this talk. So I mainly talk about thermal radiation. So there are many models available in the literature which took attempt to explain these observed features. For example, as you can see, disk is at the left panel. The disk is quite hot at the inner region, and when the accretion rate increases, it gradually shrinks. So in the right hand side, in the top panel, you can see the similar kind of picture, but the Keplerian disk at the equatorial plane entered to the hot inner region. Also, there are models which considers that this hot corona can also be situated above the disk, so that can also generate power law component. Here at the bottom right panel, you can see that along with all this disk and corona, this when the corona hard photons scattered by the disk component, it can also get absorbed and can produce different lines. These are microscopic features. So we'll also talk about that. However, as you can see in all pictures, one thing is very common, that power law component is coming from the corona and the black body component is coming from the disk, but the position of the corona is different in different models, and their origin is also not clear. So how does the corona form, and their properties like optical depth, temperature, size and height of the corona, and what is its shapes, like it's a sphere or slab or torus, is not clear yet. And also in many models it considers as a static corona, but as we see during the observation, during the outburst period, every day corona size can change. Also, we see both timing and spectral properties, but most of the models we see that either they are explaining spectral feature or timing features separately, but it is also important to explain both spectral and timing properties simultaneously. So in this talk, we will try to answer these questions. So at the beginning, we saw that angular momentum, when matter is accreting and spiraling around a black hole, it transports angular momentum due to the presence of viscosity. So how? So consider a layer of fluid A and B. They are around a black hole. So if as ring A is inside or close to the black hole, it moves faster, and B is relatively slower. So friction between them try to slow down A and speed up B. This means angular momentum A is transferred from A to B, and this is the expression that we can write or estimate the specific angular momentum of the Keplerian disk. So if ring A loses angular momentum but is forced to remain on a Keplerian orbit, it must move inward. Ring B moves outward unless it too has friction with ring C, and which has friction with D likewise. So as we can see that A and B, they have a relative velocity. If the relative velocity between these two layers increases, it can generate turbulence, and this is called the bulbous-Hawley instability or magnetorotational instability, and this can be the cause of the origin of viscosity. So in our study, we already discussed that we need angular momentum in bonded flow. So in our study, we considered flow equations with angular momentum. So the energy of the flow can be written in this way. So first term is the kinetic energy term, second term is the thermal term, and the third term is the rotation term, and the last one is the gravitational potential term. So this gravitational potential we considered as Pachynski-Witta potential, which is basically pseudo-Newtonian, and that can explain general relativistic results closely, not exactly but closely. So we consider this potential here. So mass conservation can be written in this way, and the entropy accretion rate can be given in this way as in terms of velocity, sound speed, and the radial distance. So if we differentiate equation, this first and third equation, and eliminate dx, which is basically gradient of sound speed, so we'll get dv dx in terms of numerator by denominator form. So putting denominator equals to 0, we can get the sound speed at the sonic point. So as we can see from this expression, that lambda k is basically the Keplerian angular momentum, and lambda is the angular momentum of the flow. To get a physical solution at the sonic point, C stands for quantities at the sonic point. So to get a physical solution, lambda k should be greater than lambda. That means the flow which is spiraling around a black hole is sub-Keplerian, and not necessarily it will be Keplerian always. So as matter accreting and coming closer to the black hole, gravitational force increases. At the same time, rotation also increases, and balancing of these two forces try to slow down the matter. Therefore, matter virtually stops and again starts increasing and entering into the black hole, increasing its velocity. So this discontinuous jump is called shock. So in our study, we will consider Rankine-Hugoniot shock. So for this is basically the energy balance at the shock. So this plus is for the quantities after shock, and minus is basically for before the shock. And in our study, we are considering this dissipative flow. There can be some cooling because hot photons from the Keplerian disk can be upscattered and extract energy from the corona. Therefore, the size of the corona can change. So that cooling effect we consider in our solution. Also, as jet is present, it can extract some thermal energy from the corona. So that can significantly change the behavior of the emitted spectrum. So that's why we consider mass outflow also in our solution, and this is the pressure balance condition. If we solve these three equations, considering energy and mass conservation equation, we can get shock invariant quantity in terms of Mach number just before and after shock. So if there is no dissipation in the flow, we can get this solution, this invariant quantity in terms of this. However, in presence of cooling, another extra term will come. You can see in the black this blue mark. Also, if we consider both cooling and mass loss, both the terms, this Rm dot and zeta, these terms will appear in the solution. After solving all these equations, we also estimated the outflow by inflow rate. So how much matter is coming out from the system as the outflow or jet, we can estimate if we have the flow parameters. So this R is basically the compression ratio, shock compression ratio. As we know that the velocity at the shock velocity, we see velocity jump. So this R is defined by pre-shock velocity divided by post-shock velocity. So post-shock velocity decreases after shock, that means matter is compressed, and N is the polytropic index, which is 1 by gamma minus 1. In all our calculation, we consider gamma equals to 4 by 3 relativistic flow. And here you can see theta 0 by theta I is basically the solid angle subtended by the outflow by inflow, and we consider this as a parameter F collimation in our later study. So how our flow looks like? So Keplerian disk is sitting at the equatorial plane. It has high angular momentum, high viscosity. Low angular momentum or subkeplerian flow is sitting above and below the Keplerian. Matter virtually stops due to balance between two forces and forming a shock, and this shock is basically the boundary layer of the corona or the Compton cloud, which upscatters the soft photon. The density and optical depth inside the corona changes as both accretion rate, velocity of the flow change, and matter piles up in the post-shock region. Therefore, its optical depth and temperature also change. So this is our model geometry. So in this model we did not consider jet, but later we have developed this model including jet. So based on our flow configuration, this is the geometry of the flow. As you can see, Keplerian disk, Keplerian flow, subkeplerian flow, and this is the shock. And this Keplerian soft X-rays from the Keplerian disk is scattered by the hard X-rays. And this is the corona. We call it Sen ball because this is formed by centrifugal pressure supported boundary layer. This basically the balance of gravity and centrifugal force. So the full form of Sen ball is centrifugal pressure supported boundary layer, and the height of the corona is estimated from the pressure balance or we can say the vertical radiation force and the balance of gravity. So this Keplerian disk is basically the source of soft photons. So now in our model we will see what are the model parameters and how the spectrum look like. So yeah, this is basically the geometry. So I put in short here this figure so that you can remember every time. So this disk, for the disk we need disk accretion rate, we also need mass of the black hole, we need halo component. So this is basically halo accretion rate mh dot, and we need to show this for the optical depth of the corona we need r, basically the change in velocity, and also the size of the corona, which is basically xs. So we have 5 parameters if we do not know the mass of the black hole. So what happens when outburst starts? So during the rising phase, so rising phase, when I am talking about rising phase means the outburst starts. So in the rising phase, disk rate is low but halo rate is high. That means the halo rate is basically hot flow. So hot flow rate is high, corona size is bigger, so its temperature is also high. So it can upscatter the soft photons and they become hard. When it moves to intermediate state, in a hard intermediate state, disk state gradually increases. That means the Keplerian disk, which was formed at the outer boundary of the disk, it gradually starts moving towards the black hole, and halo rate decreases. In the soft intermediate state, disk state and halo rate more or less comparable, but disk rate is little bit high. In the soft state, disk rate is much more higher than halo rate. That means corona has almost disappeared, only the Keplerian disk is present there. So this is the scenario when we vary only the accretion rate, disk accretion rate, keeping other parameters fixed. But as you can see, this is basically we have 5 parameters. So during the observation we cannot say this way that one parameter is changing, others are fixed. So it will vary in a multi-dimensional space. So how the spectra change with accretion rate? So in this case we consider that halo accretion rate is 1 and disk accretion rate is changing. Like I showed in my previous slide. So this accretion rate we increased from 0.001 Eddington rate to 0.04 and then 0.15, and we can see increasing disk rate spectrum becomes softens. So it gradually becomes like a black body and power law component just disappears. So these are there are two types of plots. One by small a, b, c. These are when we have only dissipation due to cooling. But if we consider both cooling and mass loss or outflow, we can see the softening is much faster compared to only with the cooling case. So observe diversity. What we actually observe, and because we saw from our model that we are forming corona and we have these parameters and model geometry, all these things, and we are computing the spectrum. But if we can see what we get from observation, we can fit our model to the data. So these are the observed spectral state. So this is H1743 minus 322 black hole candidate, and the data is taken from Newstar observation from RXTE observation during 2010 outburst. And you can see this color lines. This HS, this hard state was observed during 10th August 2010, and you can see the spectral slope is gradually changing when we are moving from hard state to soft state on 31st of August 2010. So these are the observed spectral state we see. So apart from this spectral properties, we can see timing properties also. For example, if we take a light curve for the same source, and we can see the counted variation with time, we cannot see much. But if we take the Fourier transform of that light curve, we can see two prominent peaks, one at 1.174 Hz and another is 2.35. So this 2.35 is almost twice that of 1.17. So basically we found 1:2 QPO frequency. So this is basically the harmonics of 1.17, but it is not necessary we get 1:2 always, or we will get two frequencies always. We can get 2:3 or 1:3, something like that, or even a single frequency. So it depends. So here I showed only one case where this 1:2 frequency is observed. So this frequency can be classified this depending on the shape of this QPO frequency profile. One can say type A, B, and C QPOs. For example, 0 to 15 Hertz QPOs can be considered type C if this full width half maximum and RMS values satisfies within this range. So in our talk, I will mostly explain about type C QPOs. Apart from this QPO frequency and spectral shapes, we can see the different variability features in the light curve. For example, you can see here periodicity after a certain time observed by RXTE, also recently observed by AstroSat. This is basically GRS 1915 plus 105 source, and it showed heartbeat kind of oscillation. So this is LaxPC and soft SXT both showed this type of oscillations. These oscillations can be due to thermal viscous instability, or the fluctuation is in mass accretion rate, or it can be due to jet or mass outflow feedback. So in our talk, in my study, I will also try to explain these variability features. So what we are trying to show? We are trying to show that the quasi-periodic oscillations or disk oscillations that we observe, it can be originated from the oscillation of the shock. We also want to check how the viscosity parameter and cooling profile change on a daily basis during the outburst time. As the spectral state change during the outburst, is there any relation between state change and viscosity parameter? If so, what is the typical value or range of the viscosity parameter to trigger the spectral states? How does corona change with cooling rate during the outburst time? We'll also estimate the mass outflow rate from the system and the variability time scale in different light curve classes. So now we'll feed the data. We have fitted H1743-322 observed during 2010 by RXTE. So this is full range data, and you can see how this outburst is progressing. So if you look at excess in the Y panel, in the Y axis, so initially corona was quite big and it gradually decreases, and in the soft state it was almost disappeared and then again gradually increase this size of the corona. Similarly, if you look at the QPO profile, as the shock location decreases, QPO frequency increases. So this is inversely correlated. And during the soft state, we did not observe any QPO frequency, and later during the declining phase, it again decreased. Yeah, and also, if you see, we fitted the data using disk blackbody and power law model also. These are the phenomenological model, but to get some idea, it is good to fit first with these models. So we can see that our total accretion rate, disk rate plus halo rate, and the disk BP and power law model fitted flux, they show similar profiles. And this, from the fitted results, you can also compare with the theoretical understanding. For example, in the bottom panel, in the bottom cartoon diagram, you can see how the corona is evolving. So initially, when shock was far from the black hole, the corona size was bigger, and it gradually decreases and it disappears. Then inverse things happens during the declining phase of the outburst. We also fitted another black hole candidate, GX339-4. This data is taken from New Star observation, Swift and New Star. So two accretion, you can see this in the left panel, the variation of accretion rate with time, and this Keplerian disk rate was always less than sub-Keplerian halo rate. So from this we can say that source did not move to soft state, rather it was in intermediate or in hard state. We fitted with our model, and in addition we added this Lauer model. This model is to take into account the relativistic effect. Yeah, so after fitting these two models to the data, we found a beautiful line profile, that iron line is skewed, and we can see it formed double peaked. One is blue shifted and the other is red shifted, and this line intensity varied between observation days. That means this highest intensity we obtained when the size of the corona was minimum. That means the disk moved very close to the black hole and relativistic effect become very important, and it skewed the break the iron line into double peak, and from the lowest marginally bound orbit value, because this Lauer model can give the inner edge of the disk, So from that inner edge of the disk, we estimated the spin parameter of the black hole, and this GX339 is a highly spinning black hole candidate. We applied the solution to AGN also recently. So we have analyzed Mercurian 335. This is Seyfert-1 galaxy, and we have only these observations, only few, and we saw that during this observation period from 2013 to 2020, the corona size changed from 44 Schwarzschild radius to 6 Schwarzschild radius, and as 6 is quite a very small value, so we can say that corona was very compact during this period. And also this the lowest corona size was achieved when accretion rate was the highest. So you can see two arrows in the right panel. So one for excess and other for MD. So when MD was maximum, excess was minimum. Also we have estimated the height of the corona from our model fitted parameters. We can also see that hardness ratio correlates with the geometry of the corona. So hardness ratio is basically the ratio of the hard photon to the soft photon. As mass is a parameter in our model, we fitted the data, from the fitting of the data, we estimated the mass around 2.88 into 10 to the 7 solar mass for the central black hole. And this mass is consistent with the optical reverberation mapping was done by Greer in 2012. So as we have theoretical spectra, model spectra from for different parameters including accretion rates and geometry and the mass of the black hole, we applied those spectral energy distribution to cloudy, considering that the hard radiation which is coming from the inner region of the disk can illuminate the surface of the disk component, so that the gas above the disk can be ionized and produce different emission lines. So in the top left panel, we considered all possible emission lines, but our interest is only with iron lines. So lines around 6.4 keV. So here we have plotted different accretion rate variations. How the iron the emission lines change with different accretion rate. In the bottom panel, we have shown only the lines around 6.5 or mainly 5.5 to 8 keV. So this in the hard state, for different value of iron abundance, we can see that iron this line set changes. So its intensity changes, and also complex lines are generated around low energy and high energy, so around 8 or around 5 keV. So this can be possible because in the hard state, the radiation which are coming from the corona is basically hard, that is high energy photons are mostly coming and illuminating the disk. Therefore it can ionize this more species, and this intensity can increase. But in the soft state, we can see a single peak only, and as the photons are not that energetic, so it did not generate any complex lines. In the right top panel, we have estimated this 5.5 to 7.2 kV between this energy range, the equivalent width of this iron line from considering Fe2 to Fe26 species. And we can see increasing accretion rate decreases the width of the line, and this is consistent with many observations for different black holes studied so far. Now we will show, if we include jet in the model, how the spectral shape and the other things will change. Yeah. So if you remember my previous slides, this cartoon diagram has changed, and you can see two jets are biconical jets are coming from the base of the corona. What we did in this case, the hard photons which was previously coming directly to us, to the observer, now they are scattered by the jet and then coming to us. Also, some fraction of the photons from the Keplerian disk are also get upscattered by the jet and then coming to us. So these two things modifies the spectral shape, and it shows some excess around above 10 keV. It is generally believed that above 10 keV, this excess can be due to reflection from the disk. But if the jet is present in some sources, this can be from the jet also. This bulk motion of the jet can downscatter these hard photons from the corona, and they can give some excess. So we have fitted new star data for GS1354 and 64 black hole candidate, and we see including jet fits the data better. From the model fitted parameters like accretion geometry and rates and the jet collimation factor, we estimate the burst time, and we see that this time is around 20 seconds for this observation. We compared our result with the literature, and we found that Januk and Charney in 2011 they analyzed this the light curve for the source, and they got 20-second variability. So this 20-second variability is consistent with our present finding. We also estimated the mass outflow by inflow ratio, which is around 12%. So outflow rate is around 12% of the inflow rate. Now we will talk about the origin of quasi-periodic oscillations. So here at top right panel, you can see the full solution of the flow. So O is basically the outer sonic point and I is basically the inner sonic point. So if we look at the arrow, so matter is coming from the outer boundary of the disk, passing through the outer sonic point and forming a shock. These transitions, three transitions, are for three different accretion rates, and then it again moves through it passes through the inner sonic point and enters into the black hole. But it is not necessary shock will be present there always. Therefore, matter can pass through outer sonic point and it can be supersonic and just enter into the black hole. However, these three transition lines are for three different accretion rates, that means for three different cooling rate. More as the accretion rate increases, this shock moves inward, that means size of the corona changes. In this lower panel, I already discussed about this QPO frequency, so I just put it for the completeness. So what happens? As we know, at the shock there can be jump in pressure and velocity and density, and also shock can generate entropy. So if the entropy at the inner sonic point is higher than the outer sonic point, then flow must pass through the inner sonic point. However, since Rankine-Hugoniot condition is not satisfied due to cooling, this shock is not steady and oscillation starts. Similarly, if the cooling time in the post-shock region becomes comparable to the compressional heating time scale, then oscillation is a must, even if Rankine-Hugoniot predicts a steady solution. Therefore, we can say that shock is very crucial because it connects both temporal properties by its oscillatory behavior, and it can also give spectral properties behaving as a corona. So cooling effect and resonance. So we estimated cooling for H1743 minus 322, that black hole candidate, and we see that in observation day from day 1 to day 8 cooling increased and the size of the corona decreased. From those fitted results and from our simulated results, we compared this observed and theoretical QPOs. So this vertical hashes are basically QPOs observed, and the horizontal hashes shows this expected QPOs. So when the cooling time scale Tc is basically the cooling time scale and Ti is basically the infall time scale or the compressional heating time scale. So we estimated this tower, the ratio of these two time scales, and we found that within 50%, like 1.5 to 0.5, our expected QPOs matches with the observed QPOs. Sorry. But in some region we can estimate QPOs, but they were not observed. So this clearly satisfies that the expected QPOs observed and expected QPOs are matching with observed QPOs. Yeah. So far we did not consider turbulence in the flow at the post-shock region. So if we consider some quantitative turbulent effect in the flow, then the pressure balance equation will change slightly. So this extra term Pt, pressure due to turbulence, will appear, and this we have just considered like some turbulent factor density times sound speed square. So mainly this turbulence we considered because of the rotation. So considering this turbulence in the flow equation, we solve our equations and estimated the QPO frequencies, and we found that including turbulence increases the parameter space. That means forming a shock, possibility of forming shock increases, but the QPO frequency decreases. So this equation for QPO frequency will change slightly, and this Ft factor will appear here, and this is basically the turbulent factor 1 over angular momentum square. Also, in this case, we consider the spin of the black hole around 0.7. We did not do any GR calculation. We have considered only pseudo-Newtonian and pseudo-Kerr potential to understand the observation. So we applied this solution to GX339-4, and we found that the QPO frequency matches well with the observed frequency, and in the right axis of this figure, the red line shows the shock compression ratio variation, and this is basically QPO frequency variation with shock location, as these are the main two parameters, XS and R. We also wanted to check how the turbulence factor changes with spin parameter. So for a given QPO frequency, we have estimated the turbulent factor Ft, and we found that increasing spin parameter, turbulence also increases. So now we will estimate the viscosity parameter, because viscosity, change in viscosity can change the accretion rate, and also it can reflect in the spectral states. So we'll estimate viscosity. So far, from our study, what we know the accretion rate, we know the size of the corona, we know the shock compression ratio changing on a daily basis. Now, what we did, as the boundary layer of the corona, which is basically the shock, can be dictated by the energy and angular momentum of the flow. We estimate QPO frequency from the radial oscillation of the shock. So we compare theoretical QPOs and observed QPOs. When the matches, we consider those angular momentums. So from that change in angular momentum and the accretion rate, if we equate this with the viscous stress x square WR phi, where WR phi is basically the pressure, local pressure of the flow. So from this we can estimate alpha SK. Alpha SK is basically the viscosity parameter for the sub-Keplerian flow. Also we can estimate the Keplerian viscosity also using this relation. So I am not going to details of these equations, but these are mainly depending on the mass accretion rates and the radial distance of the disk. So once we have estimated this viscosity parameter, we saw that it increases during the rising phase. Viscosity increases monotonically. As you can see, these lines mainly for black, pink and blue, these lines black, pink and cyan lines. So these are basically the rising phase viscosity. However, in the declining phase we can see opposite this blue line, and we see that viscosity decreases monotonically. So this satisfies the theoretical QPOs and observed QPOs also, and also consistently gives the viscosity parameter. For these 5 black hole candidates, from observation we compared our viscosity parameter and their spectral states, and we found that when the viscosity parameter is less than 0.008, it shows hard state, and between 0.008 to 0.03 it shows hard intermediate states, and above that value soft intermediate state up to 0.1. So this can show that, and also that the mass of the black holes considered here varies from 6 to around 13 solar mass. That means it mostly covers the low mass black hole binaries. So we expect that this solution will be applicable to other black holes also, which are not considered in this study. So far I discussed what I did. Now currently I am working on simulating the Fermi bubbles using Pluto. So this is basically the map of X-ray and gamma ray using Rosetta and Fermi satellites. So you can see this red line, it's a nice bubble, and also another bubble above this red one. So the origin, these are recently observed in 2021 in X-ray, and this gamma ray was observed, this Fermi bubble, long ago in 2010. So in our study we are trying to simulate these Fermi bubbles and try to constrain what should be the energy, because there are models like star formation or HENZ. They explain that the energy budget of these bubbles are quite high. It can be around 10 to the 55 or 56 arc. So we try to constrain that energy, and also we try to see the morphology, that's how other parameters like how the jet opening angle and other things can change, which can show this type of bubbles. So we are trying to do that. We also are trying to constrain that is it from the jet or it's from the star formation. Along with this, I am also trying to see how the changing look phenomena in active galactic nuclei occurs from the X-ray observation. So recently I studied NGC 1365, and we saw that the accretion rate change can show this type of changing look behavior, where we can see this change in column density or absorption line features. So we studied this NGC object, NGC 1365 this AGN, and found that when the accretion rate increases, the hydrogen column density along the line of sight is low, and we derive that this can be due to the failed wind scenario which are coming from the disk. So these are the takeaway messages. So what we observe, that increase in accretion rate increases the cooling, thus the corner sinks, spectrum softens, QPO frequency increases. Daily basis accretion rate and viscosity variations show that viscosity may be responsible for the changing accretion rates, and these are the range of viscosity parameters that can trigger different spectral states. Viscosity parameter does rise and fall and causes the cycle of the outburst. Turbulent pressure slows down the inflowing matter, thus the QPO frequency decreases. As the matter slows down, the time increases, so QPO frequency decreases. The equivalent width of the emitter line decreases with increasing accretion rate. Line intensity varies in the hard and soft states. This small scale periodicity that we can see in the light curve can be due to local effect in the disk like jet feedback or mini outburst. The bulk motion quantization by the jet, the outflowing jet, can originate some excess in the spectra above 10 keV, and it may not be by the deflection always. Thank you very much.
Thank you, Santanu, for your interesting talk. The floor is now open for question and answers. Anybody having questions can unmute and ask.
Hello, can I ask the question?
Yeah, hi Vivek.
Hi.
Yes.
Yeah, so Shantanu, like you probably mentioned about this outburst in the spectral states, but
Yes.
I probably did not understand it completely, because at least in the case of XRBs, when it goes from this hard to soft state, there is this jet line where like jets are produced, right? Like there is a triggering of this jet formations. But does that get modeled in your in this model, like
No. Yeah. So we have just implemented jet, and we are considering the whole jet as a corona and no line emission. So we are only considering the continuum spectra.
Yeah, so, but it doesn't explain that. That will be interesting to see, right? Like why, like when.
Yeah, sure. Yes, right. So yeah, we can see that in our follow-up works, right?
Yeah. And the second question is regarding this emission line modeling using Cloudy. So
yes.
Did you work that for the XRBs, right? Or is it for an AGN?
Yes. We are trying to do for AGN. So, yeah. But yeah, so actually we are trying to do, yes. Yeah.
My question is like, suppose like if you model the emission lines, and from the emissions, can you actually deduce like what spectral state the AGN is? Because like in the case of AGNs,
yes,
spectral, it is difficult to deduce the spectral state because the time scales involved are like very huge, right? Like, I mean, the XRBs.
Yeah, right. So what we can do, so we can consider different times, like in a longer time scale sets, right? So as the agent time scale is quite long, so suppose we take one or few sets for this year, and after 10 years or 5 years we can take some other sets, and we can see how this accretion rate changes to fit those lines, no?
Yeah,
So
yeah.
we
So, or else you just
Mhm.
take the different emission line ratios, then
Okay.
so then using your model try to infer, is it possible? I don't know, like I'm just I mean try to
Yes.
get what are the accretion rates.
Yeah, sure. We can definitely do that. Actually, that can show the changing loop phenomena also, no? This line ratios.
Probably, yeah.
Yeah.
Okay.
Yes, that we can definitely do that. Yes.
Okay. And in
Yeah.
your
Thanks. Yeah.
final slide, like you mentioned about equivalent width varies with accretion rate. So
Yeah.
do you mean to say like there is a effect, Baldwin effect in quasars, where like there is an anti-correlation between equivalent width and the luminosity? So does your
That we did not study. So we
no,
mainly
that's
study
optical, but maybe you are only looking at X-ray
X-ray.
line,
Yes. Yes.
lines. So, but
Yeah.
I don't know
So
whether there is any detected Baldwin effect for X-ray. Anyway,
yeah. So.
just wanted to raise that. Okay, yeah, thanks.
Thanks. Yeah.
Any other question? No, sir. No, okay.
Hello.
Hi, Shanu, it's Ravi here. Just wanted to know, like,
Yeah.
in case of, how these results basically depend on the position of the corona. So far, what you have studied is corona seems like along the disk plane, but what if the corona is like not in the disk, but like
Yeah. So
somewhere?
yeah. So basically, this corona is spherical, right? And currently it is looking like at the equatorial plane with the disk, but it can show some excess only if we take the corona just above the disk or to some arbitrary place, like in some models they consider like lamppost, like just perpendicular to the disk. So as the properties will slightly change, like temperature and optical depth, so I think it can give some excess only, so it, but the profile will remain more or less the same
I see.
if we consider corner to some other places also.
Okay. Thank you.
Yeah.
Any other question? Okay, if there are no more questions, let us thank the speaker for the interesting talk. Thank you, Santanu.
Yeah,
I will
thanks.
close the meeting now. Thank you all.
Bye.